Yes, good morning.
Good morning, ma'am.
Good morning. So all the children are having Christmas vacation and you're still in the classes, right?
Yes, ma'am.
It happens. Okay, we'll start our 15th lecture. One more topic is left out and that we'll cover in the third hour. And by that we'll complete our course. And from next week, we'll start revision classes. So I request all of you to attend the revision classes also, because that will be like a boosting dose for you. First, you have learned the concepts, and once again if you revise, I think it will invoke your secondary memory cells, and you will easily remember the topics. So all of you please attend even the revision classes. Okay, in yesterday's class we have seen what is Q function and the algorithm for learning this Q function. Q function is like learning the value of accumulated rewards, and to highlight that value, to increase that value, to keep that value maximized, so that optimal control policy can be learned by a machine. Okay, that is called as Q function. It is actually analogous or similar to V star. V star we understood as the maximum reward points that can be accumulated by an agent in an environment by taking optimal steps. Now, for that, instead of using V star, we are using Q, because in some cases, immediate rewards may not be known, or the change to the next state, what is the value accumulated in the next state, may not be known. In such cases, instead of using V star, we can directly use Q function. Q function will enable us to observe the immediate next states at every iteration and find out the best sequence of steps in order to move to the goal state. Not only moving to the goal state by taking optimal steps, but performing some optimal sequence of actions. Say it is a manufacturing unit. In order to reduce the resource utilization and increase the efficiency of the plant, or increase the productivity of the plant, or increase the profit of the plant by using lesser resources, what sequence of actions can be taken? What is the best sequence of actions in manufacturing that can be taken? Or as I said, cab scheduling services. Okay, so whenever a process is being done, how optimally it can be done. Okay, that can be made to be learned by a agent in an environment. That agent may be a machine or a robot or a game playing application. Lots of such scenarios we can consider in order to take example of an agent and train him to perform some task, right? For that, a Q learning algorithm has been given to you, and the steps in that algorithm are explained. In today's class, we'll see an illustrative example to understand that Q learning algorithm better, and also the convergence theorem, where the point of convergence is met. Means we try to estimate the Q learning function Q cap for for a state S and action A. So what would be the accumulated rewards by taking optimal sequence of actions to move from S and starting with action A? For that, what is the estimated Q function Q cap? We will note down in a table, right? For every state and action sequence, what is its estimated Q cap value. Okay, in that table, we start with random value as we learned in the Q algorithm. We initialize it with some random values, say S1, A1. We initialize them with some random values, S2, A2. Okay, all these will be initialized with either 0 or with some random values. Now, each time the robot, let us take example of a robot. Each time the robot takes some sequence of steps, What would be the accumulated rewards, Q cap? Let us calculate that. Now, finally, what is the accumulated reward value for this agent starting from state S, for this agent starting from state S1, for this same agent starting from state S2? What are the accumulated reward points? We'll check. So where is the accumulated reward point value is more? That would be the optimal sequence of steps. Okay, and how long do you perform this iteration? How long do you iteratively make the agent learn? That is till the point, that time is till the point, the values converges means this values no longer change. Okay, whenever you perform iteration, this task iteratively, all these Q cap values will be refined again and again so that it will accumulate more reward points. Say, taking a sequence of steps 1, 2, 3, it has accumulated reward points 100. Now taking steps 4, 5, 7, it is accumulating reward points 90. Now taking completely different sequence of steps, it is accumulating reward points 200. In that case, which is the best control policy here, optimal control policy here? The third one. Right? That is how iteratively this Q cap values will be refined again and again until no longer there will be any change in the values. Now, once the values attain stability, once the values doesn't change anymore, that is called as the point of convergence. Got it, students? So how that is reached, how we can explain that state of convergence with the help of a convergence theorem. Okay, that we are going to see today. Now let us take this example to illustrate the operation of the Q learning algorithm. Consider a single action taken by an agent and the corresponding refinement to Q cap, that is estimated Q value, shown in the figure. Let us see here. Now it is starting at this particular state. The agent is starting at this particular state, initial state, say S1. Okay, now when it is starting from S1 and moving further, if it moves in this direction, it is getting 73 points. And if it is moving backwards or staying in the same position, it is getting 66. Means when it is moving away from the goal, say this is the goal state. Now if it is moving away from the goal, reward points are reduced. If it is moving towards the goal, reward points are increased, right? So when it moves from this state further towards the goal state, it is getting 100 reward points because that is the optimal step to take towards the goal. Okay, but if it is moving in this downwards direction, it is getting lesser points. And that is given by the discounting factor gamma. These reward points, how they are calculated? By specifying the gamma factor, I have explained you in yesterday's class, right? It is, this reward points can be calculated as immediate reward R plus gamma T, gamma RT plus 1 plus gamma square RT plus 2 and so on, right? What did you understand from this? If an immediate reward is given at that point of time, it is RT. And in this case, reward is not known before the action is taken. That is why RT will always be 0. And when we take gamma value lying between 0 and 1, lesser gamma value indicates immediate rewards are given priority. Greater gamma values indicate delayed rewards are given higher priority. So when we take gamma equal to 0.9 for time being and calculate this, gamma here we substitute as 0.9 and the reward given at time step t plus 1, at time slice t plus 1 means little delay in giving the reward. That is, reward is given only after the action is taken by the agent, right? That is what we are assuming from beginning. In that case, say it gets 100 points for optimal step. And then any other rewards delayed further, we are just not considering them. So all of them will go on to be 0. So what will be the reward value here that is calculated? 0.9 into 100, it is 90 for taking an optimal step if there is a delay. But if it is an immediate reward, in that case, we can give it as 100. Okay, these are our assumptions. Now, when this moves in this direction away from the goal, it is getting lesser reward points, and when it is moving towards the goal, it is getting higher reward points. Okay, so when it moves, see here, when this R, the agent, let us consider the agent to be R. Now, when this R moves towards the right, observe carefully. When it moves towards the right, it is approaching its goal. It is moving towards its goal. So the point 73 now will be added with some new reward because it is taking an optimal step. So the 17 more points are added here, and the agent goes towards the goal. That is this position. Goal is in this position. Okay, now when this agent further travels towards the goal or further proceeds towards the goal, in that case, it can be given a reward of 100. But if at all it is moving away from the goal, then it will be given lesser reward based on the discounting factor that is taken. Right? So, okay, see this how Q cap value is calculated. Q cap is the estimated value of the accumulated rewards. So this Q cap for taking an action A right, understand carefully, the estimated value of Q, that is the estimated accumulated reward values for taking a step starting from S1 and towards the right, action towards the right can be calculated as, you know this formula, the immediate reward plus the discounted factor multiplied by maximum of the Q cap values for going into the next state S2. Okay, so what is the immediate reward? Because no reward is given until the action is taken, immediate reward is considered to be 0 here. Plus, what is gamma? Gamma we have taken as 0.9 multiplied by maximum of the set of actions that can be taken at that position from that state in which other directions it can move. It can move in various directions, right? So that directions is, it can move backwards. Consider this figure. It can move backwards. There the reward will be 66. It can move downwards. There the reward would be 81. If it moves towards the goal, that is rightwards, the reward would be 100. So take the maximum of that. What is maximum? 100. So 100 into 0.9, you will get 90. So that would be the new Q cap entry into the table for moving from S1 by taking an action to move towards the right. Got it? How this formula is working? You learned about this formula in the previous class. You remember? The Q cap estimated Q function value is always sum of the immediate reward plus discounted factor multiplied by the maximum of different actions that can be taken. Different rewards that can be accumulated. So it can move in the left direction, where that reward would be 66. It can move downwards, that reward would be 81, and it can move rightwards towards a goal, and that reward would be 100. Now among them, what is the maximum value? 100. So that 100 is multiplied by the discounting factor, and that will be the new value of Q estimation for moving from step S1 towards the right hand side. That is the value that should be updated into the Q cap table for state S1 if it moves towards the right. In the same way, you can calculate from state S1 moving towards down, from state S1 moving towards left, from state S1 moving towards up. moving upwards. Okay, again from state S2 moving towards left, right, down, up, and state S3 moving towards left, right, up, down. For all these states, all possible movements of the agent can be calculated and put into the table, Q cap table. Now, this Q cap table have to be iterated. See, by taking a sequence of steps, how many rewards the agent is accumulating. Now, among them, which sequence of steps accumulated more number of rewards? That would be the optimal state. That would be the optimal control policy, or that would be the optimal control sequence of steps that have to be taken. Right? But how do we know that the optimal control policy has been reached? This process will iterate again and again until no longer the Q cap values can be updated. It reaches its stable position. That would be the convergence point where we stop this Q learning algorithm and we take them as the final reward points accumulated and select the best sequence of steps from that. Not we, the machine selects the best sequence of steps from that. That is how it adaptively learns. It adapts to the environment, it gets feedback from the environment, and then corrects its steps so that it decides on an optimal control policy for that particular task. That is how a robo or any machine, autonomous machine, tries to learn by itself. Got it? Now, each time the agent moves forward from an old state to a new one, same thing I'm explaining here. Q learning propagates, Q cap estimates backwards from the new state to the old state. When the agent proceeds from old state to new state, based on its action, it propagates the feedback, it propagates the Q cap values back to the old state. At the same time, the immediate reward received by the agent for the transition is used to augment these propagated values of Q cap. So in order to update this Q cap values, this immediate reward received by the agent for the transition is used to calculate. But immediate reward, generally we assumed it to be 0 because reward is not received until the action is taken. Okay, but if there are, in some cases, if there are immediate rewards, means the agent knows what would be the reward that it can get by taking a specific action. Then that R also plays some important role in the calculation. Now consider applying this algorithm to the grid world and reward function shown in the figure. This is the figure grid world environment we have considered in yesterday's class in order to understand what are the immediate reward values and what is Q value that can be updated and what is the optimal, what is the best reward accumulated, what is the best reward values that can be accumulated. Okay, this figure I have explained you clearly in the last class, right? In this case, in this particular grid, every other step other than going towards the goal step, the reward 0 is given because entering the goal state is only the optimal step initially. Okay, so initially the rewards given are 100 and 100, and for every other move the rewards given are 0. But the agent doesn't start only in this position or in this position, right? It can start from any of these states, this state or this state or this state. That is why the Q values are modified in the next step, so that if the agent from this position moves towards the goal, it is given 90. And if it moves away from the goal, it is given 81 points. Okay, this is calculated by using the formula given for Q of SA. Now these values are updated, means what would be the reward points that can be accumulated for moving from this position. Now for moving from this position, it can accumulate reward points 90. For moving from this position, it can accumulate reward points 100. For moving to this position, it can accumulate reward points 90 because it is away from the goal. But for moving from this position to this position, again it is moving towards the goal, so it can accumulate reward points 100. But after moving to the absorbing state, that is the goal state, no more reward points can be accumulated. That is why the reward points that can be accumulated from that state is 0. Okay, this is how the reward points that can be accumulated, V star of S, can be measured, calculated. Okay, so here they are just showing the optimal sequence of steps that can be taken to reach the goal state by the agent. Now the reward is 0 here in the top grid except when entering the goal state that we have seen. Since this world contains an absorbing goal state, that is that grid world, the first grid world contains the absorbing goal state, we will assume that training consists of a series of episodes. Remember, when an agent reaches its absorbing state, it can no longer move from there, right? There is no meaning for that agent to move away from the goal state once it has reached the goal state. Consider a robot is trained to perform only one task. This is an extreme case. It doesn't happen, but for simplicity, for understanding, just consider a robot is trained to perform only one task and it has performed the task successfully. Means in this case, it has reached the goal state. Once it has reached the goal state, it has attained its objective. So it stays there infinitely. Assume like that. Now, since this world, that is this grid world, contains an absorbing goal state, means the rover has reached its final position, we will assume that training consists of a series of episodes. Let us not stop with one particular sequence of steps. In this state, the robo has moved in this direction and in this direction and it has reached the goal state. But is that the case always? No. The robo may move in this direction and in this direction and in this direction and again finally reach the goal state. There may be several directions that it can follow in order to reach the goal state. In this case, how to train the agent on every possible sequence of steps and select the best step. For that, we have to perform the training process in series of episodes. One episode indicates one sequence of steps followed by the agent to reach the goal state. Okay, so since this world contains an absorbing goal state, we'll assume that training consists of series of episodes, lots of episodes, each episode giving one sequence of steps to be followed from its current state to reach the goal state. Did you understand? I'm repeating. Episode is a sequence of steps starting from the robo starting from its current state to reach the goal state. And always it may not start from the same state, right? So try another episode, training with another episode. It starts from a different initial state and follows sequence of actions to reach the goal state. Again, in the third episode, it may start from completely different initial state and follows quick sequence of steps to reach the final goal state. Like this, the agent has to be trained on different sequences of steps, and these series of steps are called as sequence. Each sequence of steps are called as episodes. Okay, so during each episode, the agent begins at some randomly chosen state. The agent doesn't have to start from the same state again and again. That is what we want, right? We don't want the robot to behave only in a particular direction. It may come across various situations in the real time. It has to handle all that, right? It may have to start at various states, but its ultimate goal is to reach the final state. So during each episode, the agent begins at some randomly chosen state and is allowed to execute actions until it reaches the absorbing goal state. Got it? Once in first episode it starts from state S1. From in second episode it starts from state S7. In third episode it can start from state S3. But what sequence of steps it takes to reach the final goal? That is called as episode. And how many reward points in each episode are accumulated are of interest here. Okay, more reward points accumulated, more interesting is that episode, right? More useful is that episode for the agent to learn from. So when it undergoes this kind of training, the episode ends and the agent is transported to a new randomly chosen initial state for the next episode. Okay, what happens here? It starts from random state. In this case, it may start in the first episode, it may start from here. In the second episode, it may start from here. In the third episode, it can start from here. And it moves through sequence of steps and reaches the goal state. Now, in the next episode, it is made to start again randomly from a different state. Got it? Again, it is made to move towards the goal and observe the sequence of steps. Those sequence of steps are recorded in that particular episode. That is what is given here. When it undergoes that kind of training, the episode ends. The first episode may end, and the agent is transported to a entirely new, randomly chosen initial state for the next episode. Sometimes even the initial states may be repeated. Let it be. Say it may start from initial state S1, go through S3, S4, and reach the goal state. And it can again start from S1. This time it doesn't go through S3, but it goes through S2 and S4 to reach the final state. So lots of combinations are possible. Starting from S1, it can have different sequence of steps. Starting from S2, it can have different sequence of steps to reach the goal state. That is why the agent have to be trained infinitely on starting from different initial states and on sequence of actions it takes to reach the final state. Okay, so given a sufficient number of training episodes, given sufficient training to the agent, the information will propagate from the transitions with non-zero reward back through the entire state action space available to the agent, resulting eventually in a Q cap table containing the Q values. So what is happening? Whenever the agent moves from one state to the next state, immediately what is the reward it encounters will be propagated back to the previous state, and that reward is noted down there. Okay, that will enable us to capture this estimated Q function values, that is Q cap values, and those will be entered into the table. Now, this kind of training is repeated iteratively, and correspondingly the Q cap values in the table are updated. And this updation takes place until no longer there is an updation that can be made, until it reaches the point of convergence. Got it, students? Now, will the algorithm converge to a Q cap equal to true Q function? That is what I said, right? That is the question. Will the algorithm converge towards a Q cap value, that is the estimated Q function being equal to the real Q function? Means the real in the real time, whether this estimation will meet the expectation, the original value Q? The answer is yes, but under certain conditions. First, we must assume the system is a deterministic Markov decision process. What do we mean by this? I already gave you an example of this. Markov decision process means the system will decide its current state based only on immediate previous state. It doesn't depend on all the previous states, but it depends only on its immediate previous step, immediate previous state. Okay, that is called as Markov decision process. So we should assume that the system is following this Markov decision process. Only then we can answer this question whether Q cap will reach this Q value or not, will become equal to this Q value or not. Okay, so second, we must assume the immediate reward values are bounded. Means there is some higher bound. Say for all the optimal steps, we'll give some bounded value 100. And for any other step, we give discounted values 90 or 80 or 70, like this, based on the discounting factor, gamma. What did you understand from this? We have fixed the maximum value to be 100 for the optimal step that is taken. We can't simply go on giving 200, 300,000 reward points, right? For that particular training for that particular experiment, you have to decide a higher bound on the reward that can be given for optimal move. That is what is given here. We must assume the immediate reward values are bounded. That is, there exists some positive constant C. In this case, we have taken it as 100 reward points, right? Such that for all states S and action A, the reward value when the agent moves from state S by taking action A is always lesser than this bound C. That is 100 in this case. That is why when we are giving the reward points, we are giving as 100, 91, 80, 77, 66. Did you observe? All are below this constant 100. Or it depends on you. You can fix it at 200 or you can fix it at 300. But once 300 is fixed, you can't go towards giving the reward points as 500 for an optimal step. For that experiment, what is the highest bound determined? That has to be followed. Now third, we assume the agent selects actions in such a fashion that it visits every possible state action pair infinitely often. We have to assume that the agent selects actions in such a fashion that it visits every possible state action pair infinitely often. The agent has learned starting from state S1, reaching the goal point with some sequence of steps. Now in the second iteration, we need not avoid it from starting from state S1. It can start again from state S1, but this time take a different direction to reach the goal. That is different training for the agent. But this time the accumulated rewards may be more, who knows? So the agent has to go through the possible state action pairs infinitely often. It can start from S1, keep track of every possible action to reach the goal state. It can start from S2, keep track of every possible action it can take to reach the goal state G. Okay, so what it is doing is it is starting infinitely often from any of the states and learn its sequence of steps to reach the goal state. To find the optimal sequence of steps it has to follow by the end of this Q function, Q learning algorithm. Got it? By this third condition, we mean that if action A is a legal action from states S, if it is an allowed action from state S, then over time, the agent must execute action A from state S repeatedly. That is what I said. From state S1 it has started, let it start and learn from it repeatedly by following different directions each time. State S repeatedly and with non-zero frequency as the length of its action sequence approaches infinity. Sometimes it can start from S1, go to S2, again come back to S1, go to S4, then to the goal state. Lots of combinations are possible. Infinitely many combinations are possible for the agent to learn starting from a particular state. Okay, every possible state it can start with and explore in which different ways it can reach the goal state and which would be the optimal sequence of actions that it can take to accumulate more number of rewards by the end of this process. by the end of this training. Got it? Note these conditions are in some ways quite general and in others fairly restrictive, right? We are trying to generalize that it has to learn everything, and we are trying to make it more restrictive also, making the agent to learn everything. It can learn every possible sequence of actions, and it has to learn. We are actually restricting it to learn every possible sequence of actions in order to reach the final goal state. Let it be driving an autonomous vehicle, let it be checking accounts, or let it be cooking some recipe that is already pre-fed into the robo, or let it be some music sequence it has to play. For everything it has to note down, it has to get trained with what sequence of actions it can take from one state to another state to complete its task that is assigned to it by its master. Okay, for that it has to learn every possible alternative and select the best solution from that and stick to that solution. Not sticking to that solution, it can always refine that solution. Once it has found the optimal solution, it doesn't stick to that indefinitely, right? It has at that point of time learned one optimal control policy, but it is not that it can't change any further. Later it comes across a different environment where there is too much of noise around it. In that scenario, it has to play some musical notes. That time it may have to check with other sequence of actions. Other set of musical notes may have to be played. So based on the environment, this robo has to continuously enhance its learning process and continuously refine its optimal control policy. When I say optimal control policy, it is not the end for the robo. It has to learn better than that again and again based on its changing real-time environment. Got it? Now, the key idea underlying the proof of convergence is that the table entry Q cap, that is the estimated Q function value, with the largest error must have its error reduced by a factor of gamma whenever it is updated, right? How the Q cap value will be updated? Only by reducing the error that is recorded in the table. The key idea underlying the proof of convergence is that whatever table entry you make for the estimated Q function value with the largest error must have its error reduced by the discounted factor gamma. So whenever an updation takes place, that updation should be in such a way that the error of that agent learning has to be reduced. Only that kind of estimated value have to be put into the table. If the error is being increased, perform the iteration again without updating the Q cap value in the table, right? Something what you did in your post pruning, you try to reduce the error in prediction by the decision tree by refining the values, right? As another example I'll give you. Say, whenever you cut a branch from the decision tree, if it is not increasing the performance of the decision tree, keep the branch as it is. But after cutting that branch from the decision tree, if it is improving the performance of the decision tree, means it is reducing the prediction error, then it is a good decision to remove that branch, to make the decision tree as simple as possible according to your Occam's razor method. Simple decision trees are always preferred, right? So whenever you're pruning a tree, if pruning the tree increases the performance and reduces the prediction error, then prune it. Otherwise, keep the branch as it is. Do not lose essential information. Same thing we are using here. If the largest error that is encountered by the Q learning function is reduced by a factor of gamma, then you update the value. If it is not being reduced, don't update the value. Now, the reason is that its new value depends only in part on error-prone Q cap estimates, with the remainder depending on the error-free observed immediate reward R. I'll read it again. The reason is that its new value depends only in part on error-prone Q-cap estimates. Q-cap estimates are error-prone because we are just estimating by starting with a random value and finally fine-tuning them to arrive at the final convergence point. So they are highly error-prone, with the remainder depending on the error-free observed immediate reward R. This Q-cap estimated values are always dependent on the immediate reward that is encountered by taking an action. Okay, that is why we have to go towards a point of convergence by indefinitely training the agent. We can't compromise by doing some 10 iterations or 20 iterations. It has to be done repeatedly so that because this Q-cap estimate is highly error prone and it solely depends on the immediate reward that is given to the agent when some action is taken. So what is the theorem that explains this convergence of Q learning better? Let us see here. Convergence of Q learning for deterministic Markov decision processes. How is it explained by this theorem? Listen carefully. Consider a Q learning agent. An agent is learning by using Q learning approach. In a deterministic MDP, in a deterministic Markov decision process, which indicates that the current state of the agent just depends on its immediately previous state. Okay, so consider a Q learning agent in a deterministic MDP with bounded rewards. Bounded rewards means there is some maximum point that is decided for the rewards, 100 or 200 you can take. So that for every state and action pair, the reward given for moving from state S by taking an action A always will be lesser than or equal to that bounded value, that is 100 in this case. Now the Q learning agent uses the training rule of equation 1. What is the training rule of equation 1? It is given here. See, Q cap of SA, how is it calculated? It is sum of the immediate reward plus maximum of this Q cap, maximum of estimated value of Q for moving from state S in any of the directions possible, but for taking an action A. Okay, that multiplied by the discounting factor gamma. That will give you the estimation of Q cap S of A. Q cap of SA. Right? That the Q learning agent uses this training rule given in this equation. This is called as the training rule, like perceptron training rule, as I said yesterday. Perceptron training rule will help you to calculate the change in the weights in order to reduce the prediction error. Here, you are calculating the change in the estimated value so that more rewards can be accumulated, right? Optimal control policy can be decided. Now, the Q learning agent uses this training rule, equation 1 given here, initializes its table Q cap S of A to arbitrary finite values, either 0 or some random values you can take, and uses a discounting factor gamma. This gamma lies between 0 and 1, and let Q cap N SA denote the agent's hypothesis Q cap SA. So what is the final value here? After nth update, N is called as the updates number. Say some 100 updations have been done to arrive at a final optimal control policy. Now that last updation is called as Q cap N. Okay, it is denoted by Q cap N. Now let Q cap N SA denote the agent's hypothesis. That is your final state, final estimated value. That hypothesis, that denote the agent hypothesis of the estimated value Q cap following the nth update. Now, if each state action pair is visited infinitely often, as I said, it has to start from every initial state possible and explore every sequence of actions possible to meet the final goal. Understood? So if each state action pair is visited infinitely often, then what happens? Observe this. Then the nth update, that is the final update, converges to the original Q value. That is the optimal reward values that can be accumulated. The original estimated value of accumulated rewards will be same as your original rewards that can be accumulated as n tends to infinity. Means as you go on training the agent repeatedly again and again on the sequence of steps to be taken from various states, and as this updations made to the QCAP value reaches infinity, tends towards infinity, means as many number of times possible you train, as many number of times possible if you train the agent on taking different sequence of steps to reach the final goal. As it tends to infinity, the more you train the agent, then the updated QCAP value will be equal to the original Q function value for all state and action pairs. Got it? This is called the convergence theorem or convergence of Q learning. But remember, for Markov decision process only. Why? Because we are just considering only the immediately previous step, the immediately previous state. We are not considering all the previous states positions or all the previous states of that particular current state. We are just taking its immediately previous state. That is why it is called as convergence of Q learning for deterministic Markov decision processes. Got it? For this, the proof is given in the textbook, which is not required. But if you are interested, we can arrange for a separate class and I'll explain you that proof also. Okay? So understanding the basic convergence theorem is important, and that is very well explained in this slide. Now in the next class, that is your third hour now today, we'll go through experimentation strategies and updating the sequence. That will complete our course. Any doubts, students, today? Okay, then we'll meet with the next topic in the next class.